All right, let's revisit regression by talking about control variables and dummy variables in our multiple regression lines. Okay, so recalling multiple regression. Multiple regression is used to estimate the relationship between one continuous dependent variable and two or more independent variables. All right, this allows you to determine the overall fit, which is often referred to as the variance explained of the model, and the relative contribution of each of the predictors to the total variance explained. And in a nutshell, this is saying that, we're going to get some information about the variation in the dependent variable, in that continuous dependent variable. And we're going to be able to say, well, how much of that variance or variation in the dependent variable is explained by our set of independent variables. All right, and that independent variable can sometimes be referred to as a predictor variable, an explanatory variable, or a regressor. And the dependent variable can also be referred to as an outcome, a target variable, a criterion variable, and a response variable. All right, so we are going to have a sample of data, right? And the sample is drawn from a population. The goal of our regression line is to estimate the regression line for the population. So in terms of the parameters, we can see an example here of a multiple regression line with a dependent variable and 3 independent variables, where beta naught or beta 0 is the constant parameter. So this would be the constant or intercept for the entire population. Beta 1 would be the slope parameter for the independent variable x1. And beta 2 would be the slope parameter for the independent variable x2, and so forth. And then epsilon represents the population errors or residuals. All right, and so then for our sample drawn from our population, we have our multiple regression line where we have our statistics, now in terms of lowercase b's and little e, that are estimating the beta and the epsilon parameters. And so we have B0, which is our sample intercept, B1, or B sub 1, which is the sample slope coefficient for the independent variable x1, and the same with B2 and B3 for the independent variables x2 and x3 respectively. And we have E, which is the sample errors and residuals for our regression line. Confidence intervals can then be calculated for the sample intercept and slopes. All right, so we'll have like a confidence, can have a confidence interval to estimate the range for our possible parameters. And predictions can also be made based on the calculated regression line. All right, so to be able to run a multiple regression, what assumptions must be met? First, as already stated, the dependent variable must be continuous. So the dependent variable must be either interval or ratio data. And there must be 2 or more independent variables, and these independent variables can be continuous or nominal. All right, as far as running the regression beyond just demands on the dependent and independent variables, we also have to have independence of errors, a linear relationship between the predictors and the dependent variable, homoscedasticity of the residuals, and homoscedasticity is simply saying equal error variances. There can be no multicollinearity. There can be no or minimal significant outliers. And the errors are normally distributed. Oops. All right, so now let's go into these with a little bit more detail. So what do I mean by, for example, independence of errors? Independence of errors says there's no relationship or correlation between the residuals and the dependent variable. In JASP, we're going to use a test called the Durbin-Watson test to check for this independence. This Durbin-Watson test is a test for correlation in the residuals. The statistic ranges from 0 to 4, where a value of 2 indicates no correlation. Values from 0 to less than 2 suggest positive correlation, and values from greater than 2 to 4 suggest negative correlation. All right, so what's going to be a value that says, okay, we can move forward and assume independence of errors? And the answer is we're typically going to assume independence of errors when we see a value between 1 and 3. All right, multicollinearity occurs when there are high correlations between 2 or more independent variables. You'll oftentimes hear this referred to as redundancy. Oftentimes we struggle having reading achievement and writing achievement in our model as predictors, because reading achievement and writing achievement sometimes can be extremely highly correlated. But the big question is, how high is too high? Well, in JASP, we can examine tolerance and the variance inflation factor. Tolerance is 1 minus the coefficient of determination of a regression of predictor J on all other predictors. And the variance inflation factor is the inverse of the tolerance. Ideally, we need the tolerance to be greater than 0.2 and the variance inflation factor to be less than 5. Notice I say ideally, and this is where, sometimes with statistics we make judgment calls, because you'll hear ideally we want this greater than 0.2 and less than 5, but the absolute cutoff is that tolerance has to be greater than 0.1 and the variance inflation factor has to be less than 10. All right, outliers. Too many outliers can have an impact on the model by skewing the results, and this includes skewing your estimated slopes as well as your intercept. All right, one way to determine if outliers may be present is looking at the residual. All right, and again, just going back, reminding you about this word residual, keep in mind that for any y, all right, there is a observed y value for the given x values, and then there is a predicted y value for the given x values. The difference between the observed and predicted is a residual. All right, and obviously we want those residuals very small, indicating that our predictions are very close to our observations. Now, if our observations are very far away, right, then we're going to end up with large residuals because the predicted value of y is not going to be so far away. The predicted value of y will not be an outlier. All right, so we assume the residuals are normally distributed, which we'll get to a little bit more in a minute. All right, and so the residuals, and remember with a normal distribution, we kind of keep everything within 3 standard deviations. So residuals that are 3 or more standard deviations from the mean is potentially bad. In JASP, we're going to get case-wise diagnostics to examine the residuals that are far, meaning greater than or equal to 3 standard deviations from the mean. What do we do with outliers? And this is a million-dollar question here. There's a lot of controversy and a debate in how to handle outliers. All right. The first thing you want to do if you think you have an outlier, if our case-wise diagnostics suggest an outlier, we may want to go back to our original data and see, hey, do we have a typo or a mistake in the original data? If this isn't due to a typo or a mistake, then we need to take a look at our sample size. All right. When sample sizes are extremely large, all right, so into the thousands, we expect some outliers. All right, and in this case, we definitely do not want to discard the outliers We just don't want a lot of outliers. However, if we have a small sample size and we have outliers, we do in fact have a problem. One option is something called Winsorizing, which replaces the outlier value with the maximum minimum found after removing the outlier. But again, we can still have data integrity issues. What we definitely do not want to do is delete the outliers, especially if we have small data sets. All right, homoscedasticity of residuals or equal error variances. The variance of the residuals is the same for all values of the independent variables. We check this assumption by examining the residuals versus predicted plot. All right, and so I have an example of a residuals versus predictive plot over on the right-hand side of the screen. And what we should see is a balanced distribution of the residuals around the baseline. You'll often hear me say, hey, this should look like random scatter. If the plot shows a pattern, i.e. not random scatter, then the variances are not consistent. And in this situation, in our image on the right, we definitely see a pattern. We see this kind of quadratic or parabola pattern, and that's a problem. And this suggests that we are violating the equal error variances assumption. All right, the other plot we're going to look at in our output is the QQ plot. All right, the QQ plot can show if there's a linear relationship between the predictors and the dependent variable, and it also serves to show if the errors are normally distributed. We can check this assumption by looking at our plot, and so I have two QQ plots over on the right-hand side of the screen. All right, and the standardized residual should fit along the diagonal. So in the first plot on the left, we see where the residuals fit nicely along the diagonal. And so here we can assume linearity and normality of the errors. However, on the QQ plot on the right, we see this deviation from the diagonal, right, on both ends. And so this is suggesting that either we have an issue with the normality of the errors or the linearity of the relationship between the predictors and the dependent variable. All right, so let's talk about dummy variables that sometimes can be referred to as indicator variables. Many times we want to include categorical or nominal variables in a regression. Examples can include race, ethnicity, college major, marital status. And we need to create dummy variables to represent the presence, or absence of some categorical effect. You will always create n-1 dummy variables for a variable within categories. For example, if we have a sample with 5 college majors, then we will create 4 dummy variables. One category will always be our referent group. When the dummy variable takes on the value of 1, its coefficient serves to alter the intercept. Consider a very simple example where we wish to predict salary from age and gender. All right, and so here we have our line of salary is equal to the intercept plus the slope times age plus the slope times female. And here, female is a 1 in our data set and male is a 0 in our data set. And let's just pretend for a second that we get our results and have our line with our values filled in for the intercept and slopes. All right, for females, the intercept decreases by $400. So if we want to think about this line in terms of female salary, then female salary would be equal to $20,600, plus $1,500 times age. And so what this value of minus 400 is doing is it's taking the male line, all right, and shifting it down by $400. How do we create dummy variables in Excel? In our data file, we have a variable called locale, and I'll pull this up in just here. I will move our PowerPoint over just a little bit, and I'm going to open our data set. And so here we see in column D, we have a variable called locale, where 1 equals urban, 2 equals suburban, and 3 equals rural. We wish to create 2 dummy variables for the suburban and rural categories, thus that making urban our referent group. In Excel, we need 2 new variables, suburban and rural. So I'm going to come over here to column M, and I'm going to say suburban and rural. All right, and what we need here is we need some logic. So for suburban, which takes on the value of 2, we need a formula that says if locale equals 2, then give me a 1, signifying suburban. Otherwise, give me a 0. All right, and so what we type here, this is just an if statement. And so we type equals if, and I'm going to go over here to locale, so cell D2. So if locale equals 2, comma, give me a 1, signifying true. Otherwise, give me a 0, signifying false. And I'm going to close my parentheses, and notice I get a 0, right? Because in M2, the locale is urban, or 1, so it is not suburban, so I get a 0. You can either drag this, you can grab this little green square and drag it down, or you can double click on it and it automatically does the if statement for all of the students in the sample. All right, we want to do the same thing for rural, but now rural takes on the value of 3, so we'll say equals if locale, so the value in M2, if that equals 3, now that is true. Otherwise, I want a 0 because it's false. All right, and again, we see for this first one that urban takes on the value of 0 because it is not rural. All right, and I can double click the little green box and I get all my values. All right, and I want to show you how to save a file as a CSV. So we're going to go into File, Save As. All right, and I am going to call this ELS example 1. And again, you want to say, if I had given you an Excel file and I asked you to save it as a CSV, because in JASP we can only, one of the file types we can open are the comma separated value files, or CSVs. We could save as a comma separated values, or we can save as the MS-DOS. Sometimes we have issues in software saving as the Macintosh comma separated file. So I'm going to say comma separated values and save this. Okay, and that is how we create dummy variables. For locale, we now have 2 dummy variables, suburban and rural. All right, and we can go back to our PowerPoint. All right, and now let's talk about control variables. To properly measure the relationship between a dependent variable and an independent variable, extraneous or confounding variables must be controlled. Control variables are not of central interest to the study, but ignoring the variables could skew results. Including control variables can enhance the internal validity of the study. All right, so what do I mean by that? It helps you establish a correlational or causal relationship between your variables of interest depending on your research design. All right, let's think of an example here. So we wish to explore whether there is a relationship between income and happiness. What other factors are likely to influence our results? So what are some other variables we are going to want in our model, right, that might also explain, that may also contribute to happiness? All right, we might want age, physical health, mental health, marital status, and we can certainly think of others. But again, these are possible extraneous or confounding variables that we want to make sure are in the model, all right? And this is referred to as controlling for these variables. All right, so let's do an example from the Education Longitudinal Study of 2002. All right, we can use a multiple regression to understand whether 10th grade math performance can be predicted by math self-efficacy, instrumental motivation, and sex. All right, self-efficacy, this variable represents, how well the student thinks he or she can do in math. Because this is a national data set, this is federal data, it has been mean-centered. It's been standardized to a mean of 0 and a standard deviation of 1, and it is continuous. So it kind of looks like z-scores. The same with instrumental motivation. Instrumental motivation is also thought of as utility and interest kind of put together. Motivation to perform well academically in order to satisfy external goals like future job opportunities or financial security. All right, and again, it is also standardized to a mean of 0 and a standard deviation of 1. And sex in this data set is dichotomous, where male is 0 and female is 1. Our goal is to determine how much variation in 10th grade math performance can be explained by self-efficacy, instrumental motivation, and sex as a whole, and also the relative contribution of each of these independent variables. All right, so this is the line that we want to estimate. So let's run the regression in JASP, all right, and I'm going to... All right, and so what we want to do is we want to open this ELS example 1 CSV in JASP. So I'm going over to JASP. And before we open the file, for those of you that have not already done so, all right, we want to make sure we have all of our missing values that I tend to use added to our missing value list. So if you don't have -99 added to the list, all right, make sure you type in here -99 and add it to your list for missing variables. All right, otherwise we can open our ELS example 1 data file. All right, and notice in the CSV, you'll see -99, but since JASP recognizes that as a missing value, we see these blank or missing cells. All right, so we want to run a regression. All right, so I'm going to try to split screen a little bit here. We want to run a regression, a linear regression, where math achievement is our dependent variable. And then we see covariates and factors. And JASP with these little faded symbols is telling us what to put where. So covariates are for continuous, which is the ruler, or ordinal data, all right? And factors are for nominal or categorical data and also ordinal data. So ordinal, it's a little bit of a debate whether we want to put that in as a covariate or whether we want to put that as a factor. We will talk a little bit more about that later. But in general, if we're dealing with Likert scales, we have research that suggests that if we have 5 or more points, we can put that data here in as a covariate. Typically, if we have 4 scale points or fewer, then that is going to go in here as a factor. Now, one thing to be careful about is JASP doesn't always recognize the correct data type. So notice here we have race, ethnicity that JASP is thinking is ordinal data, but that's only because in this data set it's coded as 1, 2, 3, 4. All right, but that represents 4 different race ethnicities, and so it is definitely nominal and would go in here as a factor. All right, so we've got math achievement as our dependent variable. We're going to have instrumental motivation and math self-efficacy as our covariates. We want to go under statistics, and we want to check collinearity diagnostics, and we want to check all 3 boxes under residuals. We also want to go under plots, and we want to check residuals versus predicted, and QQ plot standardized residuals. All right, so first, are our assumptions met? So let's start over here. All right, and we are going to start with our first output in the model summary. We get the Durbin-Watson results. We're going to look at our alternative hypothesis, which the null hypothesis is only the Y. It's the null model, no predictors. And H1 is our tested model with the 2 predictors, instrumental motivation and self-efficacy. And we want to look over at the Durbin-Watson statistic, and we see 1.598. That is a value between 1 and 3. And so we feel like we can assume independence of errors. All right, as for multicollinearity, we can go down to our coefficients table, and we see the collinearity statistics. We see that the tolerance for both of our predictors is greater than 0.2, and the VIF for both of our predictors is less than 5. And so here our ideal conditions are met, and we can assume that we do not have multicollinearity. All right, what about the outliers? So let's scroll down to our case-wise diagnostics. And what we see here are 14 potential outliers. And so these are our case numbers, right, for the students. And we see that the standardized residual is greater than or less than 3, greater than 3 or less than -3. All right, indicating a possible outlier. But we have 16,000 students in this data set, and we're seeing only 14 potential outliers. We are working with such a large data set that we don't need to worry about these 14 cases. We can move forward. All right, let's look at our plots. All right, our residual versus predicted plot does in fact look like random scatter around our baseline. We do not see any discernible pattern, and so we can assume equal error variances or homoscedasticity. With our QQ plot, we see that the standardized residuals follow nicely along the diagonal. There's a little bit of a deviation up at the top, but by and large, we are on that diagonal. And so we can make the assumption of linearity between the predictors and the dependent variable, as well as normality of the errors. All this to say, we can move forward and actually look at the output of our regression. All right, so let's go back up here to the first table. And the first thing I'm going to look at is the adjusted R squared, this 0.165. All right, and this is telling me that, you know what? I just realized I left female out of the equation. So let's add female in. All right, and again, our assumptions are still met. But we see this adjusted R squared of 0.167. How do we interpret that? What that's telling us is that 16.7% of the variation in math achievement is explained by instrumental motivation, math self-efficacy, and sex. Right? We then go to our ANOVA table and we see an F statistic with a p-value of less than 0.001. This is the omnibus test, and this is telling us that at least one of our three predictors explains a significant amount of the variation in 10th grade math achievement. So it's saying that at least one of these three predictors is good. All right, let's go down to our coefficients table. And we can look at our alternative. We're not interested in the null model. We are interested only in the alternative model here. And we see that everything has a significant p-value. All right, so the intercept, instrumental motivation, math self-efficacy, and sex are all significant. All right, and we can see that we have a intercept value of 52.02. What is this saying? This says that males with average instrumental motivation, I can actually go ahead and, males with average instrumental motivation and average self-efficacy, so values of 0, right, on the motivation and self-efficacy, and here the value of 0 means average. Males with these average values are predicted to have a math achievement score of 52.02. All right, what about females? How does this change for females? Females with average instrumental motivation and average self-efficacy are predicted to have a math achievement score of 52.02 minus 0.936, giving us 51.08. So we see that the female line for 10th grade math achievement is shifted down by 0.936 achievement points. All right, we could write the equation of our line using our unstandardized coefficients and intercept such that math achievement is equal to 52.02 plus 2.842 times math self-efficacy plus 1.46 times instrumental motivation minus 0.936 times female. We can also look at the standardized output. Standardized coefficients for our continuous variables are interpreted as changes in standard deviation. So let's go back for a second and think about interpreting the unstandardized coefficient for math self-efficacy. What 2.842 is telling us is that for a 1 unit increase in math self-efficacy, there is a 2.842 increase in 10th grade math achievement. The standardized coefficient is interpreted as a standard deviation. So what that's saying is that for a standard deviation increase in math self-efficacy, we get a 0.289 standard deviation increase in 10th grade math achievement. All right. Again, this allows us to think about changes when variables are on different scales. All right. This is also, the standardized coefficients are sometimes referred to as effect sizes, where 0.1 is small, 0.3 is medium, and 0.5 is large. Here we see for math self-efficacy of that value of 0.289, telling us that it's a small to medium, very close to medium effect on 10th grade math achievement. All right, what if we want to add another variable? So we created dummy variables for suburban and rural. Let's add those to our model now. So let's go back to our model and add suburban as a factor and add rural as a factor. All right, and so it's updating for us, it's running this. Okay, so now we can see in our coefficients table that this includes suburban and rural. I want to show you something quickly in JASP before we go back to that. So we do have the locale variable. Is JASP smart enough to recognize the categorical nature of locale? So if I add it as a factor, I do get our dummy variables, and these unstandardized coefficients match what we will see with our dummy variables, suburban and rural. All right, so we have locale 2 here would be suburban, and locale 3 here would be rural. So if the base category, all right, is your referent group that you want, so here we wanted urban, which is the base category, then we can just simply put locale into the model. The problem occurs when we want something else as our referent group. So if we had wanted suburban as the referent group, then we're in a situation where we have to create dummy variables. All right, but I am going to take locale back out, and I'm going to put suburban and rural back in. And I'm waiting on our model to update. Okay. So just very quickly, we still see our Durbin-Watson statistic is appropriately between 1 and 3. Our tolerance is above 0.2. Our VIF is below 5, so we can assume no multicollinearity. We do not have a high number of outliers, especially given how large our data set is. We still have random scatter of our residuals versus predicted values, suggesting homoscedasticity. And our QQ plot still suggests we can assume linearity between our predictors and our dependent variable, as well as normally distributed errors. All right, so let's go back. All right, so I am now going to go back to our slideshow. All right, so again, we put in suburban and rural. All right, and let's take a look at our output now. All right, so our line changes a bit. All right, so now we have math achievement is equal to our intercept of 51.829 plus 2.837 times math self-efficacy plus 1.464 times instrumental motivation minus 0.936 times female plus 5.81 times suburban minus 5.63 times rural. Okay, so that is our line written out, but what is all of this saying? The intercept of 51.829 is now the predicted math achievement for a male in an urban locale with average math self-efficacy and average instrumental motivation. All right, so we notice that if we want to interpret this line for males in a suburban environment, right, we see that the intercept increases by 0.581. If we want to interpret this line for males in a rural environment, we see that the line shifts down by 0.563. If we want to interpret this line for a female in a rural environment, then the line shifts down by 0.36 plus 0.563. So it's shifting down by about 0.15. All right, let's go to the classwork now and work on some problems in JASP.